Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Today we're going to talk about asymptotes. F is a given function and C is the representative curve of F in an orthonormal system. Now C is going to have a vertical asymptote if and only if the limit of f of x as x tends to a is infinity. And C will have a horizontal asymptote whose equation is y equals b if and only if the limit of f of x as x tends to infinity is b. And C will have point I whose coordinates are a, b as a limiting point or an endpoint if and only if the limit of f of x as x tends to a is b. And finally, C will have an oblique asymptote whose equation is y equals ax plus b if and only if the limit of f of x as x tends to infinity is infinity and the limit as x tends to infinity of f of x minus y is 0. Now let's take an example about a vertical asymptote. We have the function f and C is its representative curve. Remember, x equals a is a vertical asymptote if and only if the limit as x tends to a is infinity. Now the question is to determine this limit and to give a graphical interpretation for the obtained result. Now the limit is plus infinity, and this is because if we substitute 1 we get 2 over 0, and in this case is it 0 plus or 0 minus? Remember, we draw a sign table for x minus 1, opposite sign, and 1 plus means to the right of 1, this is the right of 1, and in this case x minus 1 is positive, so we will have 0 plus. So we can say from here that C has a vertical asymptote whose equation is x equals 1. So why do we have a vertical asymptote? Because when x tends to a constant, the answer is infinity. Let's see it graphically. Now this is x equals 1, which is a vertical line. Now this is the way we deal with vertical asymptotes. So when x is 1 plus to the right of 1, you see the difference between the curve and the asymptote would tend to 0. Now let's see an application. This is the function, C is its curve. The question is to verify that x equals 2 is an asymptote to C, and it will be here vertical because x equals 2 is a vertical line. The limit as x tends to 2 minus of this function is, if we substitute 2, we get 5 minus the limit of this quantity at 2 minus, which is plus infinity. In fact, we have here 1 over 0 minus. And the limit as x tends to 2 plus is negative infinity, because we have 1 over 0 plus. And from here, we can tell that D is a vertical asymptote to C, and D is the line whose equation is x equals 2. Now pay attention here please. To verify that a line is a vertical asymptote to a curve, it's enough to verify it using the limit at a minus only or at a plus only. Now here what I did is I found the limit at 2 minus and at 2 plus. It suffices to find the limit at 2 minus only or at 2 plus. Now let's see some applications about the horizontal asymptote. We have a function, C is its curve. Remember, y equals b is a horizontal asymptote if and only if the limit as x tends to infinity is b. The question is to determine the limit as x tends to plus infinity of the function and give a graphical interpretation for the obtained result. Now the limit as x tends to plus infinity of x plus 1 over x minus 1, we have plus infinity over plus infinity. So this is the limit of x over x using the leading term, or we can also use L'Hopital's rule here, and this is 1. So the limit when x tends to infinity is a constant. We can tell that we're going to have a horizontal asymptote whose equation is y equals 1. Pay attention, this is what we call the graphical interpretation of the obtained result. But now I'm going to show you how do we represent it graphically. Now, this is y equals 1, which is horizontal. This is y equals 1, which is a horizontal line, and this is the way we deal with horizontal asymptotes. You see, when x is plus infinity, the distance between the asymptote and the curve tends to 0. They are very close to each other. Let's see this application. We have this function. The question is to verify that C has a horizontal asymptote whose equation is to be determined. Now, if we find the limit at plus infinity, this one comes out and we have the limit of this quantity. Using the leading term, this becomes 3, so we have 1 minus 3, which is negative 2. So the limit at infinity is negative 2. Now the limit at minus infinity would also be negative 2. So from here we can tell that the line y equals 2 is a horizontal asymptote. Now similarly, it's enough to find the limit at plus infinity alone or at minus infinity alone. Now what is a limiting point? Let's see. Remember, the point I whose coordinates are a, b is a limiting point if and only if the limit as x tends to a of the function f of x is b. Now this is a function, and the question is to determine the limit of f of x as x tends to 3 and to give an interpretation of the obtained result. Now the limit as x tends to 3 is the limit of this quantity as x tends to 3. Now if we substitute, we get 0 over 0, so we can apply either L'Hopital's rule or the simplification method. If we take x in common, we get x minus 3 over x minus 3. If we simplify by x minus 3, we get the limit of x as x tends to 3, which is 3. So finally, the limit as x tends to 3 is 3. So we can tell that the point A, whose coordinates are 3, 3, is a limiting point or an endpoint to C. Now let's see. Remember, this is the graphical interpretation, but let's see how do we represent it graphically. It means that the point 3, 3 is a limiting point. This is an opened point. You see, this is a point that is not on the curve. And now we draw the curve, and the curve in this case is in fact a straight line because the function is y equals x. Okay? But the representative curve would be the whole straight line y equals x except point 3, 3. So this is an open point. Now another application about the limiting point or the endpoint. This is the function f. And we need first to verify that x squared plus 10x minus 39 is x minus 3 into x plus 13. Let's expand and we get this quantity. The second part asks to verify that C has a limiting point whose coordinates are to be determined. Now remember, this is the domain of definition. So if we find the limit at 3 plus, this would be the limit of the square root of this quantity. Now if we use this relation that was verified before and we replace x squared plus 10x minus 39 by x minus 3 into x plus 13, we can simplify by x minus 3, and this becomes the limit of the square root of x plus 13, which is 4. So by now we know that the limit as x tends to 3 plus is 4. And similarly for the limit as x tends to 3 minus, and we can tell from here that the point E34 is a limiting point to C. Remember again, it's enough to find one of these two limits. Now oblique asymptote, remember the line y equals ax plus b is an oblique asymptote if and only if the limit at infinity of the function is infinity and the limit at infinity of f of x minus y of d, which is y of the line, is 0. Now the given here is that we have a function f whose curve is c and we have a line d whose equation is y equals x plus 1. Now the question is to verify that d is an asymptote to c at minus infinity. You see here we have to take the limit at minus infinity. Now the limit at minus infinity of f of x is the limit of x squared over x minus 1 at minus infinity. Now using the leading term or L'Hopital's rule, we get the limit of x squared over x, which is the limit of x, which is minus infinity. So the limit at one of the two infinities leads to negative infinity. Now we find the limit of f of x minus y of d as x tends to minus infinity. Now we should have the same kind of infinities here. This would be the limit of x squared over x minus 1 minus x plus 1, and x plus 1 comes from the equation of the line. If we simplify, we get the limit of 1 over x minus 1, and 1 over infinity is 0. So the two conditions are satisfied. The limit at infinity is infinity, and the limit of f of x minus y of the line is 0. From here, we can tell that D is an oblique asymptote to C. Now let's see it graphically. Well, we have the line y equals x plus 1, and we have the curve. You see the meaning of an oblique asymptote means that when x tends to minus infinity, the distance between the line and the curve tends to 0. They are going to be very close to each other. Now let's see another application about the oblique asymptote. We have a function f whose curve is c, and we need to verify that the line L, whose equation is y equals 2x plus 1, is an asymptote to c at plus infinity and minus infinity, knowing that the limit of f at plus infinity is plus infinity and the limit of f at minus infinity is minus infinity. So here we need to verify that L is an oblique asymptote. Now take your time. Now the limit here of f of x minus y of L as x tends to plus infinity is the limit of this quantity, which is the limit of 1 over x minus 2, which is 0. And this happens because we have 1 over plus infinity. And similarly here, when x tends to negative infinity, we have 1 over negative infinity, which is also 0. So from here, we can deduce that L is an oblique asymptote to C at plus infinity and at minus infinity. Now remember here, you don't have to verify the first condition because it's given. Now Rima or Amir, let's see. We have a function f whose representative curve is c, and we need to verify that the line y equals 1 is an asymptote to c. Now let's see. Rima, the limit of the function as x tends to positive infinity is the limit of x squared over x squared, which is 1. Therefore, the line y equals 1 is an asymptote to c. Amir, the limit of the function as x tends to 1 plus leads to 2 over 0 plus, which is plus infinity. So y equals 1 is an asymptote to c. Now, which method is correct and what is the mistake in the second one? Now, I think that Rima's method is correct because when we want y equals 1 to be an asymptote, this is a horizontal line, so we need to search for the horizontal asymptote, and the formula for the horizontal asymptote is the limit at infinity leads to a constant. So this is what happens here. In fact, here this is not wrong, but in this case we cannot deduce that y equals 1 is an asymptote to c, but we can deduce that x equals 1 is a vertical asymptote to c. So Amir is answering another question. Thank you.